Okay, hello everyone. Welcome to the first seminar of the year. Kicking off our calendar for this year is Milena who's coming to us from a very, very early time in Stockholm, where she's a postdoctoral fellow at the Oscar Klein Center in Stockholm. Um, and Milena has been working a lot on Fermi and dark matter and gamma rays. And I guess today we're going to hear something along those lines under the title of the dark matters of the universe. So thank you, Milena, for getting up very early to, to present this seminar for us. And I will pass over to you.
First of all, thank you for the introduction and thank you for having me and for giving me your time. As my title suggests, I will be talking about the dark matters of the universe. And hopefully, by the end of this presentation, we will have some maybe brightness coming into the dark matters of the universe, in particular, through the gamma ray window into the dark matter that we see in the universe. In particular, I'm going to focus on an instrument, Fermi-LAT, and the results that have been obtained throughout the last almost 16 years of the Fermi-LAT searches for dark matter. To start off, I want to tell this story through 3 points of view. First off, we have a theorist's point of view. And I don't want to be presumptuous to tell to this room what theory of dark matter is, except to say that we have a very wide range of the properties that the theoretical dark matter models can follow. And in particular, I want to emphasize that the dark matter can span over 70 orders in magnitude in mass, and just as many orders of magnitude of interaction strength. And if this if this doesn't really ring a bell as to how big 70 orders of magnitude is, to bring a comparison to the room, 70 orders of magnitude is approximately difference in mass between a mass of a proton and the mass of the entire observable universe. So quite literally, when we're searching for dark matter particles, we are really searching a universally broad range of properties. And as such, seeing that we have a really broad range of properties to probe, we have to start somewhere. And the issue with having to start somewhere is that our search strategies will be inherently biased. Of course, the theoretical assumptions and theory guides where we search for these dark matter signatures, and of course that depends on models that we use to describe those signatures. We also live in a world where we make observations using various instruments, and we have the limited access to instrumentational technology. And as such, we have a disparity between the data that we have and data that we actually need, introducing an observational bias into our searches. I also want to point out that observational data also informs the theory that we come up with. And as such, there's also almost a little bit of a vicious circle going on between the first 2 points. The final point that I want to point out is that we are searching for some observable signature of the dark matter existence. And as such, we are biasing ourselves towards the dark matter models that will have some identifiable signature in our potentially electromagnetic or gravitational wave, neutrino, or cosmic ray observations. But as I said, we have to start somewhere, and Fermi-LAT is an example of an instrument that helped us probe some of the favorite theorists' models. From an observer point of view, which I'm an observer, so I feel more comfortable telling the story of this side of this point of view. We have a very wide range of masses as well as electromagnetic signatures that we can search for. And in this talk, I want to emphasize the gamma ray searches, which narrows down our favorite dark matter models to QCD axion and ALPS, WIMPs, and primordial black holes. As this talk will be focusing on Fermi-LAT, in large part, the story here will be surrounding WIMPs, but I will touch upon some of the ALP searches too. From the instrumentationalist point of view, now this is a different question to ask. When I worked with a number of instrumentation people, it's very interesting to see what they do on a daily basis. They actually build instruments, and they don't necessarily think about the most pressing science questions that we want to answer on a daily basis. More what they spend time thinking about is how to make the technologies answer those questions and also work in a way that it can provide accurate data. And what I'm showing here is the current state of the instrumentation in the high energy sky, including cosmic rays, neutrinos, gravitational waves, where we're pretty nicely covered for the upcoming future. But also I want to point out that space-based gamma rays as well as X-rays have a gap coming up where there's some uncertainty as to what kind of observatories will or can come up and will be provided funding in the future. I will come back to this plot a little later, and hopefully we can all engage in a discussion and conversation surrounding the future of the space-based gamma ray astronomy. So let's talk about where does the story of Fermi start. So Fermi-LAT is one of the instruments on board Fermi. And indeed, Fermi-LAT, as one of its main science questions, tackled the existence of the weakly interacting massive particle, or WIMP. So this was one of the main science goals driving the existence, the creation of Fermi-LAT. Now, in addition to our three main characters, I also want to tell a story of the entire scientific community as to how the astronomy was done in the past and is also currently being done. And that is through community efforts to identify the most important questions of a given decade and the instrumental needs that we require in order to tackle those questions. And as such, here, this is from the US point of view. So this is a report commissioned by a gamma ray astronomy program working group that tackled the question in 1996 as to where the next decade of gamma ray astronomy is. And one of the highest priority recommendations was the next generation 10 MeV to 100 GeV gamma ray emission, such as GLAST, that is the old name for Fermi, with orders of magnitude improvements in sensitivity compared to previous missions. And this was a community-driven effort that was presented to the governing agencies, and as such was the step towards ensuring that the future of gamma ray astronomy, space-based gamma ray astronomy at the time actually exists. And it's a beautifully written report. I really enjoyed reading it, and it can be found on the link below. I'm bringing this report to you to say that the community involvement is important because the recommendation that came from this report was a direct pathway towards building Fermi. The Fermi, as I mentioned before, has two instruments on board. There's the Fermi-LAT, which is a large area telescope placed somewhere in this white box. The second instrument on board, which I want to talk about, is GBM, or Gamma Ray Burst Monitor, which primarily focuses on transient sky. The Fermi-LAT is a pair conversion telescope that receives individual gamma rays that convert into positron-electron pairs that are then whose tracks are then detected and localized, and their deposited energy is measured so well that we can track back the source of this original gamma ray. It also Fermi-LAT also detects electrons. This is a noise for some people, but also something that can be used as data tackling some of the questions of the propagation of particles in the high energy sky. The energy range covered by Fermi-LAT spans about 20 MeV to 300 GeV, which is ideally suited for WIMP searches. The field of view is about a fifth of the sky at any time, and it covers the entire sky about every 3 hours. The single photon angular resolution is about 1 degree at 1 GeV, but what we really care about is the point source localization, which goes down to less than 0.5 arc minutes for a point source, which is unprecedented for the gamma ray detector of this kind. If you're interested in time-dependent searches with Fermi-LAT, the timing accuracy is about 1 microsecond, which gives you a decent timing resolution to study potentially some of the transient skies, such as blazar variability or potentially gamma ray bursts that are also prime targets for searches for new physics. As I mentioned before, here's a paper following the, right around the time when Fermi-LAT was launched, that was indicating that one of the things that Fermi will be very good at doing is the search for dark matter signatures for a large class of WIMP models. And indeed, that's what it did. And just to kind of motivate this, again, from the point of view of an observer, and just a very common diagram that you often see is that two WIMP particles annihilating and then producing some standard model particles that can result in final states of positrons and electrons, which can be observed by a number of different instruments, including Fermi, but also primarily AMSO2, and also in the past with Pamela. We can also have neutrino signatures from WIMP interactions, and a wide range of neutrino detectors is also active and is collecting data that also provides very interesting searches for dark matter particles. But finally, what I want to point out is that in each of these interactions, a byproduct is a gamma ray photon, and a number of different instruments can detect those. And here I also mention some of the CTAs that operate in higher energies. So the two main ways to search for the gamma ray emission from the dark matter annihilation or decay is through satellites. And right now we have Fermi that also was for a part of its lifetime working together with Agile, which was deorbited in 24. And in this energy range, Fermi is a very unique instrument. Then we also have the Cherenkov telescope arrays, which are on Earth instruments that use atmosphere or water as their calorimeter and detect particle showers in order to track back the gamma ray sources. Fermi is so unique. Here I show you the energy range of the different gamma ray observatories. Fermi is so unique that it is the only instrument that covers the low MeV to tens of GeV sky. And I do want to point out that Fermi was launched in 2008, and as such, may be coming to a later stage of its lifetime. And as such, I really hope to convince you that it's important to have something in the sky in the coming years that may potentially be the next space-based gamma ray observatory. Let's now talk about WIMPs as a primary dark matter target for Fermi. So as you all know, the dark matter gamma ray flux from WIMPs is a very attractive way to search for dark matter, and that is because the contributions from the astrophysical properties of the astrophysical objects and the contributions from the particle physics are very nicely separated. So much so that we can effectively separately model these two contributions, and such have different independent uncertainties coming when it comes to modeling these. From the dark matter targets, when it comes to Fermi-LAT, some of the most studied targets include the galactic center, the galactic center halo, dwarf spheroidal galaxies, extragalactic and galactic diffuse emission, as well as galaxy clusters. Of course, these sources are attractive either because they are expected to have high dark matter densities, or in addition to high dark matter densities, they also have lower astrophysical backgrounds. However, in the last few years, some of very interesting dark matter targets have come forward, and this is was primarily done in the papers of Rebecca Lean and Tim Linden, including the solar system, including Sun and Jupiter, brown dwarfs, as well as exoplanets. And this is actually really, I think these papers are really interesting and creative in that we're starting to use other celestial bodies as indirect dark matter detectors. When we look at the Fermi data, this is what it kind of looks like. So on the left, I show an example signal. This is an NFW dark matter annihilation signal, and an example background. And as is the case with most observations, astronomical observations, there's a part of art that comes into, there's a little bit of an artistic decision as to how much of the observation do you need with Fermi. If you're looking for point sources, you will use longer exposure times, as is shown on the top of this plot. So you see that the point sources start to dominate for this example signal in the background. But as you start decreasing the exposure time, of course, the diffuse emission will start dominating. And this is kind of the question that is become very challenging with Fermi-LAT analysis. If you're looking for diffuse dark matter signals, you will also start seeing a lot of diffuse emission coming from the classical astrophysical processes, including the cosmic ray interactions with the gas and dust in the galactic plane. But if you're looking for point-like sources, the exposure time you can increase, with the caveat that those sources are further away, and thus you have a harder time disentangling the morphology and the luminosity of those sources. And as such, the first target, and probably the most discussed target from the Fermi-LAT searches, is of course the galactic center. Now, you've already heard about the story of the galactic center gamma ray excess from Rebecca Lean, and I would strongly recommend that you listen to this recording of her talk. But I will touch upon some of the state of the current searches for the dark matter in the galactic center, and whether actually those searches can come to resolution with the current instrumental limits. So, as you may already know, the gamma ray excess coming from the galactic center is a well-established bright excess in gamma rays that peaks at around 1 to 3 GeV. It is well detected in LAT, and it was detected soon after LAT's launch in 2009, and then later reconfirmed many times in a number of different papers. Its emission is extended, and it extends up to 10 degrees or 1.5 kiloparsecs, which to someone may look like a good explanation for potentially having a dark matter signal coming from the galactic center. The reason to believe that the galactic center excess could be accounted for by dark matter annihilation is one, the morphology is approximately spherical and it extends far out of the center. So here these plots show the spectra of the galactic center excess, and we see that this intensity can be well fitted by a dark matter particle, but also we see that the spectrum is seemingly doesn't change with the position and shape. So this this diagram here shows you the galactic center and different regions considered. And then on the bottom here, we see that this peak persists from different regions in the galactic center volume. However, we don't necessarily have to resort to new physics in order to explain this. There's almost kind of a two-team division between the groups that kind of argue for a dark matter explanation of the galactic center excess, as well groups that argue for the emission from the populations of unresolved sources that we already know exist. And one of those sources that has been established as a potential source of galactic center excess is a large population of millisecond pulsars that could collectively explain this excess. The spectral the motivation for the millisecond pulsars also comes from the spectral properties of the millisecond pulsar emission. But also another thing that can be done when thinking about the individual sources is the morphology of such emission. So for example, the dark matter signal is expected to be smooth, whereas point sources are clumpy. And as such, there are some very nice techniques developed to search for the smoothness of the signal coming from the galactic center, some including the non-Poisson template fitting and wavelength transport, so thinking in Fourier space. Now, the next thing that we can say is, well, maybe it's both. And to me, that is probably the most likely explanation. However, where are we now in terms of trying to address that question? Well, the data has been there for a while. The Fermi-LAT data has been there for a while, and the techniques that have been used to characterize this galactic center excess have been incredibly creative, and some of the really most nicest work in the gamma ray astronomy that I've personally encountered. However, it may be the case that we're maybe reaching the limit of our instrument. So there's been a few papers coming out in the last few months where the authors have employed the machine learning approaches. And the gamma ray astronomy is an extremely exciting venue for machine learning, but also very complicated, seeing that the training sets for machine learning algorithms may not necessarily be sizable enough to compete with other observational data. However, in the case of the galactic center excess, that is seeing that it's a very unique signature, uniquely observed in gamma rays, it is also a place for development of very nice machine learning approaches. And in those machine learning approaches, the kind of the approach is similar to the more traditional Bayesian analysis, where the authors ask whether the total profile looks more like millisecond pulsars or dark matter, or does it look lumpy or smooth? And again, here we don't reach a conclusive result. So in addition to potentially reaching the instrumental limits of Fermi-LAT, we also have a really big problem when it comes to the galactic center excess, in that the major source of uncertainty comes from the modeling of the galactic diffuse background. And this is where the theoretical models and data don't match. So this is also something that has to be studied in more detail in order to be able to characterize the galactic center excess. So if we kind of maybe think that Fermi-LAT has done its job when it comes to observing the galactic center excess, and the only path forward maybe is improving the galactic diffuse models, what other things do we have left with the current Fermi-LAT observations? Well, in order to confirm pulsars, Fermi-LAT does not have the necessary angular resolution to resolve those, but we have a number of radio instruments that are either existent or coming on board soon, and in particular, future detections of radio emission coming from pulsars in the galactic center by MeerKAT and SKA can help navigate this problem. If we want to confirm dark matter, at this time, maybe one path forward is to check for signals in other places. And as such, this brings me to target number 2, which are dwarf spheroidal galaxies. Dwarf spheroidal galaxies are, as the name suggests, small galaxies, satellites of the Milky Way, specifically in these surges are satellites of the Milky Way, and have large dark matter content, however, have very low astrophysical backgrounds. Now, these are very attractive sources because, as I said, they have high dark matter content and low astrophysical backgrounds, but also that means that they are very faint. So they are also hard to observe with Fermi-LAT. And this is also something that has been covered, maybe not through the Fermi-LAT lens, but also the dwarf spheroidal galaxy dark matter halo modeling and profile modeling, as well as the nature of the gamma ray emission in dwarf spheroidal galaxies has been discussed previously at the CPPC seminars. But I will bring the Fermi-LAT point of view. Now, just to bring back, the dark matter gamma ray flux comes from the astrophysics J factor and the particle physics that the modeling coming from the particle physics in dwarf spheroidal galaxies too, of course. And I want to emphasize this again because the astrophysics J factor comes as an important ingredient in the searches for dwarf spheroidal galaxies. The astrophysics J factor basically measures the dark matter content in the line of sight between us and the given source. And this is important for any extragalactic dark matter target. On the top, I show the dwarf galaxies that have either already been detected or predicted to be detected predicted to be redetected in the future optical surveys. And the reason why I say that is because the Fermi-LAT has been relying mostly on the increased number of sources as the time progressed, in addition to the increased exposure with time. So the Fermi collaboration has done a number of analyses spanning different time ranges, but also different number of targets. On the right side here, I show you the kind of the detection TS profiles, or the detection significance profiles, as a function of the dark matter WIMP dark matter mass for different number of sources as well as different Fermi exposure time. And I want to draw your attention to, well, maybe the green line here, which is comes from reticulum 2, for example, and it shows somewhat significant TS max of about 8, which translates into 2 point something sigma. Similar result has been found in 2024. This is a combined likelihood analysis with an increased maximum TS at around a few hundred GeV dark matter mass. Now, this is what it looks like in comparison when thinking about the different Fermi-LAT collaboration results. So in 2017, the Fermi-LAT found, well, I wouldn't say found, but identified a statistical significance of a less than 2 sigma. As we increased the number of sources and exposure, it reached about 2 sigma. To the last paper from Fermi-LAT collaboration indicates that this is kind of steadily increasing statistical significance. Another interesting thing that shows up in these plots, in addition to the statistical considerations, is also the placement of the peak. So of the TS peak or the test statistic peak, we see that there's a slight shift towards higher dark matter masses. Now, this is not well understood or understood at all, but it is also something that hopefully will be addressed primarily with a higher number of dwarf spheroidal galaxies that we're expected to see in the future. Now, when putting the dwarf spheroidal galaxies in context of other searches, the trials factors reduce the significance to about half a sigma. But what is important, so what you can do then is put some upper limits, which are generally consistent for 2024, generally consistent with the previous dwarf limits. So the dashed line here shows the 2024 limit in coming from the dwarf spheroidal galaxies, excluding all the parameter space above it, and is embedded in a 95% confidence level of the yellow band. And what is interesting here is that if the galactic center excess was accounted for by dark matter annihilation, then the observations from dwarf spheroidal galaxies are in tension with such an observation. However, as I mentioned before, we cannot rule out the dark matter explanation of the galactic center excess solely by dwarf spheroidal galaxies yet, because of the uncertainties in the modeling of the galactic center excess analysis. Now, another thing that I want to point out is the J factor considerations in the dwarf spheroidal galaxy searches. Here I show you for the last paper from the Fermi-LAT collaboration in 2024, a number of dwarf spheroidal galaxies that have been considered, and the J factors that have been computed either using optical observations or dynamical measurements to describe them. And I do want to point out that the J factors calculations have many underlying assumptions that cause a larger spread in their values, and some of those include, of course, the dark matter distribution models, but also the approach of using a parametric or non-parametric approaches to describe them, as well as our observational limitations. And these uncertainties can result in at least a factor of few difference, and in some cases, order of magnitude difference in the real value of the J factor, which, if we look back to this plot, would kind of bring the galactic center and the dwarf spheroidal galaxies in the same part of the parameter space. Now, what is the future of the dwarf spheroidal dark matter searches? One may argue that the future really lies in increasing the number of sources. So here I show a plot of the predicted number of dwarf spheroidal galaxies that we expect to see from, for example, LSST, or instruments that have that are in building stages and soon to be operating. And we see that the number of dwarf spheroidal galaxies will reach hundreds in the coming decade or so. What does that mean for the Fermi-LAT searches? On the right, I show the plot of the local significance of the dwarf spheroidal galaxy signal as a function of number of years considered in Fermi-LAT data, and the increasing number of dwarf spheroidal galaxies. So we see that for about 12 years of Fermi-LAT data, we can reach a 5 sigma significance if we get around 65 additional 65 dwarf spheroidal galaxies, which, based on this plot, is doable. Now, this also relies upon, we don't only need to detect these dwarf spheroidal galaxies, we also need to characterize those J factors. And that also brings in a little bit of uncertainty when it comes to the plot on the right. But I want to ask you a question, and the question is, how many dwarf galaxies do we really need? If, for example, we keep adding dwarf galaxies, at some point we will we will start running out of them, and as we start putting in more and more systems whose morphologies might be differing to the extent that it's really hard to describe them, maybe what we can do instead is find but just a really good one, and characterize it really well. And that is the example of what we did with Ursa Major 3. The Ursa Major 3 is recently discovered likely dwarf spheroidal galaxy that is very nearby our own galaxy. It's at around 10 kiloparsecs, and it has a relatively low number of the stars that constitute it. However, the argument that has been used to describe its dark matter content is that unless it has a large dark matter density, it would have been tidally disrupted by the galactic, by our own galaxy, which brings to a really large value for the J factor, which then can provide very strong constraints on the dark matter annihilation. So here I show you on the right, the usual cross-section versus the dark matter mass plot, and I want you to focus on the black line indicating the point source coming from the, assuming a point source for the Ursa Major 3, and this excludes values for the canonical thermal cross, assuming a canonical thermal cross section, the values of the WIMP masses below about 2 TeV. This is a very strong limit, on the orders of about an order of magnitude stronger than the dwarf stacking limit, but also by and large excludes the galactic center excess to be described as dark matter annihilation. Now, this is a very strong statement. However, it relies upon a very strong assumption that the Ursa Major dark matter content is actually correctly calculated. Confirming the dark matter density of this source requires observations, the kinematics observations of its star members, and that is something that future optical instruments will provide us with. So one final thing that I want to mention about dwarf spheroidal galaxies is something called the glory duck. And the name for this comes from actually one of the I believe, collaboration meetings that were held in Berlin, where a bunch of people ate at a Glory Duck restaurant in Berlin and came up with the idea to set up a software, a pipeline to perform multi-instrument and multi-target analysis using various instrumentation and observation techniques. Now, this ideally would kind of provide the most sensitive and most robust results. However, what we find is that joining likelihoods across different instruments is really challenging. One, because the response functions are collectively hard to combine, and two, because the usual statistical analysis techniques across different instruments may differ. So how do you combine binned or versus unbinned analysis and so on and so forth? However, for this project, the first focus were the dwarf spheroidal galaxies. And as expected, the limits were driven by LAT sensitivity in most of the mass range for the WIMP dark matter. However, what is really exciting about this project, this is soon to be published, and the code is going to be publicly available, is that it is a legacy analysis of the current generation gamma ray instruments, and it's a beautiful setup for the future gamma ray observatories, including CTA and so on, as well as CTA. So here I show you the Glory Duck upper limits on the dark matter, on the WIMP dark matter mass. So the black line shows the total, the joint likelihood upper limit for different annihilation channels, and the different dashed lines come from different instruments. Now, the red dashed line is the Fermi-LAT, and you can see that for the most of the mass range, it overlaps with the total likelihood. And so you can say that these regions are very heavily dominated by Fermi-LAT, as expected, since Fermi's LAT sensitivity and the angular resolution at those energies at lower masses will be better compared to the CTAs. On the other hand, this is the high mass dark matter models are taken over by the CTAs at higher energies, of course. But this is really an exciting. Maybe in this case, maybe it is maybe hard to make an argument that combining these instruments brings better upper limits. But really, the point that I want to make is that maybe in the case, for example, for the BB channel, maybe it would have been good with just using Fermi-LAT, but really kind of with the future missions, as we expand upon the energy coverage and the angular resolution and so on, combining the analysis might have stronger consequences. And this is the example of the dwarf spheroidal galaxies. These can also be applied to other dark matter WIMP targets, so such as subhalo stellar streams, dwarfs, dark matter spikes, and so on and so forth. Now, the third target that I want to talk about, and I will touch upon very briefly, are the galaxy clusters. Galaxy clusters are very exciting dark matter structures. However, they're also, unfortunately, very rich in the classical astrophysical processes that can result in gamma ray and X-ray, will result in X-ray emission and potentially result in gamma ray emission. Some of the galaxy clusters have very messy and very diverse galaxy members. Some of them have AGNs, which we do expect to emit gamma rays. So a really hard side of galaxy cluster searches for dark matter comes from really our difficulties with separating the dark matter signal from the classical astrophysical backgrounds. Nevertheless, these efforts have been completed, and I want to emphasize the work by Di Mauro et al. In 2023, where they report actually marginal detection of the gamma rays from galaxy clusters and exclude indicate the dark matter mass range that could potentially account for such access. Interestingly, these such masses and cross sections have already been excluded by dwarf spheroidal galaxies, and also are not corresponding to the galactic center axis. Nevertheless, it's an interesting result that needs a further exploration. Having said that, I have not seen any papers that have reproduced this excess. So even though it is a collaboration work, I would take it a bit carefully and maybe reconsider the underlying assumptions that are coming from the modeling of the astrophysical backgrounds. In our paper that we recently submitted, we show on the right another use of the galaxy cluster observations in gamma rays to put some of the most stringent limits on the dark matter WIMP particle. And here, what we are assuming on the right is that the survival of so-called prompt cusps, which are these high density dark matter mini halos formed very early on in the universe and survived through the galactic times, could contribute very dominantly to the gamma ray annihilation signal, even though they don't contribute much to the overall mass of the dark matter in the galaxy clusters. And this argument helps us really, of course, provide some of the strong limits, excluding the intention with the galactic center axis and improving the dwarf spheroidal limit by almost an order of magnitude at some parts, and being consistent at higher masses. I want to very briefly talk about axions and ALPS. I am sure you are all very well aware of the axion and ALPS searches with the Fermi-LAT, but I do want to mention a few maybe biased, interesting things that you can do with Fermi-LAT and the axion-like particles. And in particular, that is the use of the Fermi-LAT's temporal resolution and searches for axion-like particles in the transient sky. So one of the ideas that has been very widely recognized and used in axion-like particle searches is using the observations of core collapse supernovae. And the idea here is that at the time of the core collapse of a massive star, the thermal photons that are abundantly produced in these environments will be converted into axion-like particles via Primakov process, and then seeing that they're weakly interacting particles will travel undisturbed until they reach the next strong magnetic field, which is the Milky Way's magnetic field in many research papers, and will be converted into gamma rays, which will result in a very unique spectral shape in the prompt gamma ray emission of a core collapse supernova. And this is a smoking gun signature for axion-like particles, because we don't know of any other physical processes that are predicted to produce such a signature on these timescales. So the signature of axion-like particle emission is shown on the right here, and we see that the peak happens on the 70 to 100 MeV, depending on the progenitor mass. Now, this, if you remember the LAT energy coverage from 20 MeV to a few hundreds of GeV, we see that this signature peak happens at the lower energy regime, where the LAT's effective area is much smaller. So there are some very nice techniques that can be applied on background rejection in this energy range to salvage some of the potential signal that may come in these energy bins. And now, from other point of view, the core collapse supernovae are one of the very hot topics in the optical astronomy, in that we have an abundance of the new ones coming in weekly in ZTF tests, and also some of the older running instruments. I will say that the axion-like particles can be probed in gamma ray observations in many other venues, including the galactic sources, potentially pulsars, neutron stars, extragalactic GRBs through the extragalactic background light absorption, and oscillations below critical energy. And here I put forward some of the people that have really worked on the Fermi-LAT observations of the axion-like particles. And an example here is also the observation, an example of the upper limit plot for an axion-like particle. This is coming from Mayer and Petruszewska in 2020, and this is an example of using the core collapse supernovae to search for the axion-like particles. The Fermi-LAT constraints, unfortunately, are not necessarily the strongest ones. And the stronger ones actually come from the X-ray observations of galaxy clusters for these light axion-like particles. I want to also mention my favorite GRB, 221009. That's a very unoriginal thing to say, I guess, in the transient community, that the brightest GRB is my favorite. But this was a big event that happened in 2022 where the entire transient astronomy community went really in on it. It was an extraordinary event from GRB at a redshift of 0.15 that resulted in some of the very interesting searches for new physics. And I want to emphasize that actually soon after the discovery, I think it was maybe 2 days after the discovery, there was the first paper that came out about this GRB, and it was on axion-like particles, which is quite an achievement, thinking that people were competing against transient astronomy, people who are putting out notices on mostly like on the order of hours basis. However, the interesting part of this GRB is not only that it was very bright, it is also that it was observed in very high energies. And in particular, there was an observation of an 18 and maybe about 200 TeV emission from this GRB. And in fact, there was a paper yesterday that came out talking about the likelihood of this multi-hundred TeV emission. However, through the interactions of gamma rays with the background lights, this shouldn't have happened. We would expect that the extragalactic background light would attenuate the gamma rays of these high energies, and so much so that the probability of finding this photon in our detector is incredibly low, and potentially could be described by some new physics processes, and some of the most popular options were axion-like particles. On the left, I showed the probability produced by Galanti et al. As a function of energy of the observed photon energy And we see that there's a really steep drop at around a few TeV. On the right, I show quite a wide range in the upper limits coming from this observation. And I want to emphasize that these have to be really carefully done because the energy resolution of these instruments is very limited. And as such, claiming that something is an 18 TeV photon also kind of really spans that that the energy, potential energy of this photon could be on the order of a few TeV to where we see that the probability increases pretty quickly. Probability of survival increases pretty quickly. So the kind of ALP searches with these instruments should be very carefully done, and especially at these higher energies. Now, I want to bring back something about the axion-like particles and the core collapse supernovae in that instead, if we want to search for the kind of the spectral peak coming from the core collapse supernovae, we need a sensitive instrument in the MeV energy range. And here I show you the current and the past observatories that have provided some of the very exciting observations in the gamma ray sky. However, we have not have had much success in proposing and building instruments in the MeV energy range. First, because it's very hard from the instrumental point of view to come up with a technology that will be sensitive to MEV photons, but also because we have been kind of relying on the Fermi's ability to maybe reach some of the MEV emission. However, I just showed one example of the MEV emission that could be potentially interesting. I'm sure you all can come up, think of your favorite MEV observable signature that may not include the transient emission from core collapse supernovae, maybe potentially even including some of the multi-messenger binary neutron star mergers or some other sources that you can search for. And as such, I think it's of incredible importance to get together as a community and figure out a way to push for MEV potentially, or a really gamma ray instrument to be covering this energy range. So where do we go next from here? This is something that I think it's really maybe representative of the dark matter searches. And it's so expecting to uncover dark matter in the next 2 decades is like waiting for the sun during a Stockholm winter, and it's not fun, I must say. But if you catch a glimpse, it's barely enough to brighten your day before the darkness takes over again. So it doesn't seem to be very bright, as per ChatGPT. ChatGPT's a little bit of a guided answer. But maybe there is hope. Coming back to this plot where we don't really see anything coming up in the next Fermi-LAT energy range, there is a community effort that has been ongoing in identifying, again, the most important and most pressing questions for the next few decades that can be uniquely answered by gamma ray observations. As of now, we don't have an instrument that will be covering the energy range in the few tens of MeV to GeV regions after Fermi-LAT. And also, even though Fermi is an exceptional and outstanding observatory, it is also uncertain as to where the funding will be coming from and whether it will be continued following the senior review that should happen this year. Then I also want to bring to you a little bit of gamma ray astronomy history. Here's a plot from 1968 from the orbiting solar observatory at around 50 MeV. And I love this plot. It shows doesn't really show the photons, but shows the density of the gamma ray observations, indicated by the density of lines that have improved so much in the last decade. So here we have COMTEL in 1 to 30 MeV, egret, and this beautiful Fermi-LAT, this should be 2020, I apologize, which is above to 500 MeV. And these efforts have come from, as a result of community efforts put forward. And as such, I want to maybe give a little plug about the FIGSAG and maybe invite you to think about what your most pressing and most exciting question is that could be answered by the space-based gamma ray astronomy. We are currently in the process of writing the report. Please reach out personally to me if you are interested in any specific segments of the report or joining on the effort. I will say I'm now awfully becoming aware that this is being recorded, but I will say that this effort has been temporarily paused by NASA. Not only this effort, but all the science analysis groups from all the wavelengths have been temporarily paused as to review any of the activities that may be going not in line with the most current political executive order decisions. But we hope to be back relatively soon and to continue working on this large community effort again. So with that, I want to kind of maybe pause for a second and pose a question and asking, where does this story end and where does this leave us? What's the Fermi-LAT's legacy in the gamma ray astronomy when it comes to dark matter searches? Now, as I started being involved with the kind of the idea of future gamma ray astronomy, a future of the gamma ray astronomy, it's very interesting to see what the community thinks about whether Fermi-LAT was successful or not in the context of dark matter searches. One of the reasons why Fermi-LAT was selected was because it made a strong argument that it will detect a weakly interacting massive particle. If you ask that question, by no means was Fermi-LAT successful. However, in my opinion, it is one of the instruments that has provided an incredible wealth of knowledge as to what dark matter particle, WIMP dark matter particle, and others are not. Whether that's valuable knowledge, I think in our community, it's not hard to argue that it is, but it's becoming very obvious to me that other communities don't necessarily see it as such. So I would like to invite you all to maybe help me convince the gamma ray astronomers that dark matter is, even though we haven't detected it yet, is a very exciting venue to pitch when it comes to the space-based gamma ray astronomy. And I will leave you with some conclusions, very brief conclusions, and very top level, and say that the gamma ray observations provide unique tests for different dark matter models. Indirect detection provides stringent constraints, as we've seen in a few cases. And hopefully I've convinced you that the future experiment development is crucial and that this effort for the future experiments really comes from, really is driven by the community efforts. And an example of which we can see in the exoplanet community, for example. And as well as that our next space gamma ray experiment is uncertain. And I hope that some of you can reach out to me about the specifics of FIGSAG. As I said, temporarily paused, and so I don't want to really dwell upon it, but I want you to know that this effort exists and is an important effort for the future of the space-based gamma ray astronomy. And with that, I'm going to stop talking and thank you for your attention. And I guess I'm going to open the floor for any questions you might have. Thank you all.
Thank you very much. Questions? Roland.
Can I ask one question?
Yeah, no, you go ahead.
I wanted to ask about the galactic center access and those 4 spheroidal limits.
Yes.
Can you go back to those slides when you first discussed the 12 spheroidal limit?
This one maybe, or this one?
Yeah, this one is good.
Yes.
So first of all, okay, maybe it answers already. I was just wondering what's the annihilation cross-section is into BB bar, is that right? Was
yes.
that always the assumption for all the figures?
Was that always the assumption for all the figures?
Yeah,
no.
About the galactic center access, or?
Yeah, no. There's usually, I guess maybe I am biased into. Usually, I present the BB bar, but there's been work there. All of these papers also report annihilation into W and tau tau annihilation channels too, and all. I believe all of those two are in tension with the galactic center access.
So the other thing, but how it looked like, it's really now in tension. The dark matter explanation of the galactic center access tension with multiple of those measurements, right?
Yes, that is true. However, I do want to emphasize that the galactic center is an extremely messy region of the gamma ray sky. And the modeling, so the background in the gamma ray sky comes from the cosmic ray propagations within the galactic plane, interacting with gas and dust. And we just don't have a good, well, we have more better gas maps and dust maps, but we don't really understand the propagation of the cosmic rays that we put into our models. And as such, we may be underestimating or overestimating the amount of background we have. Okay, so the main uncertainty here comes. Yeah, exactly. Okay, yeah, thank you.
Roland.
Thanks for the talk, Milena. Yeah, I'm going to object a little bit. I think your account of the GC excess doesn't give proper credit to work which has been based on template analysis.
Okay.
So I mean, I've been involved in that, but I mean, Chris Gordon, who's also watching, and his former student Oscar Macias, for instance, and then also Bartels et al. Even if we can't ever, find point sources contributing, basically statistically, it could just be because the millisecond pulsars are just very old and dim, right? But the work that we've been involved with for many years now shows with increasing confidence that spatially that signal traces the stars in the bulge.
Thank you, Roland, for that comment, and I apologize if I miscredited your work. I do believe that there's I think at some point asking whether there's a from the dark matter point of view, arguing that all the millisecond pulsars, for example, follow a power law or something like that is a very simplistic thing to say. And so there's been a lot of work done from the dark matter point of view to ask how many of those pulsars do you really need to account for this excess? And again, with this very naive assumption that the millisecond pulsars emit in power law in gamma rays, you get to points where it's on the order of a few tens of thousands of those millisecond pulsars. And then at some point, from my point of view, you got to start asking, what does it really mean for the dark matter signal, for example, in the discussions between the smooth and clumpy? What does it really mean to have, say, 70,000, 80,000 millisecond pulsars in this much of a volume? And will we ever be able to actually resolve those populations? Like whether the approach of kind of maybe even template fitting and so on, also the dark matter modeling, whether those approaches can actually account for the large populations of these milliseconds. Like you can make millisecond pulsars go dimmer and dimmer and dimmer until some point it just becomes a smooth distributions that can be described by dark matter too. What can we do there? I think that I personally think the answer is not in gamma rays. The answer should be in other wavelengths. But yeah, I apologize if I miscredited and maybe had somewhat of a dark matter biased view of it. I am very much aware of it.
Okay, no worries. Thanks.
Yeah.
Chris?
Thanks. Yeah, Roland's covered the galactic center excess part, but I also wanted to ask about your Ursa Major results. You
Yes.
mentioned that it was going to be possible to test whether the dwarf galaxy had been tidally disrupted. Could you say a bit about how that's going to be tested?
So really the way that it's been done right now is there are 11, if I'm correct, there are currently 11 star members of this dwarf spheroidal galaxy that have been observed by an infrared instrument. And in kind of removing some of the members of these of this supposed dwarf galaxy results in a complete kind of dismantle of this system as a potential dwarf spheroidal galaxy. What you need to do in order to test for these whether these stars are actually belonging to this dwarf spheroidal galaxy is have a good spectral measurement as well as the kinematics measurement. So Gaia, for example, would be a kind of observatory that would be ideal if it is able to reach those distances, and it potentially is, according to Gaia people. But I guess in the future, ideally, what we would want to do is really probe the kinematics of the system.
Thank you.
Thank you.
Yara?
Yeah, thank you for your talk, by the way. I was just wondering, I keep seeing people talk about obviously the gamma ray access, and I don't work in this. I was just wondering if you have any idea of what would tip the balance towards it being dark matter or not. What would be like a definitive sort of piece of evidence to rule it out or in?
So I think, thank you for the question. So I think there's kind of in my mind, the most definitive answer to that question would be if we found dark matter somewhere else. So for example, if we search for dark matter emission from different systems that are better characterized in the galactic center excess in gamma rays, one way to discriminate against the galactic center excess dark matter explanation is, for example, the dwarf spheroidal galaxies or galaxy clusters. Having said that, we are dealing with a large number of uncertainties in those models too. The second approach, I believe, is a definite detection of the other sources in other wavelengths. So that's kind of the discussions that we previously had, for example, radio emission and so on and so forth. I think it would be very interesting if we had a sensitive enough instrument to, for example, test the galactic center emission from nearby galaxies, Andromeda, for example. I think it would be very interesting to see whether this is universal across different galaxies or not. And maybe that could be an indicator about the universality of the dark matter explanation may be more independent than across different galaxy types. I think the most realistic one would probably be with the current instruments, I would say the radio astronomy will help a lot in maybe identifying some of the sources that could potentially account for galactic center excess that are not dark matter.
Thank you so much.
That's a hard question.
Sorry.
Thank you. No, I gave you many options.
Yeah, no, that's great.
I'm not very convinced with many of them, but I do think that I would be excited to see whether this exists in, say, Andromeda or something like that, and see how the properties of the emission compare to Milky Way, the fact that it's maybe spherically symmetric or not, whether that translates across different galaxy populations.
Thank you so much.
To follow up on that, I'm sure people study this, but there must, on the theory side, there must be ways to try and reconcile the galactic center excess with the non-observation in dorsal-roidals. Like if you just introduce some velocity dependence, you should have higher dark matter velocities in the galactic center and lower dark matter velocities in a dorsal-roidal, I would imagine. But does that not sort of move the constraint up and move the galactic center excess down? I mean, this is the kind of game that board theorists play all the time, so I'm sure these studies exist, but I'm not aware of them.
Yeah, I'm not sure. I would have to check in on that.
Can I also, I don't want to take up too much time, but I do also want to quickly ask about the prompt cusps
Yes.
plot that you showed. I spotted this paper on the archive. I have not read it yet. Are the lines that you're drawing here like an apples to apples comparison? I mean, are you also reanalyzing dorsal-roidals and the galactic center excess in the context of prompt cusps as well?
That's a very good question. Thank you for asking. It is apples to apples. The reason for that is that the prompt cusps would not necessarily affect the emission from the dorsal-roidals and the galactic center excess, because we're looking at the central regions of these objects, which are dominated by very large dark matter densities. The prompt cusps in Virgo cluster actually reside not necessarily in the very central region, but more in the outskirts. So those would not necessarily be at the those will contribute to the large structures, but not so much to the small dense regions considered in the galactic center excess and dorsal-roidals.
So you've incorporated some modeling of like how much tidal disruption has gone on, but depending on where the contrasts are residing in these structures, yeah.
Yes, the tidal, exactly. We show in the paper that tidal disruption has minimal effects for the cases of galaxy clusters. There's one thing that we don't do in our paper, and hopefully we can do in the future, and that is the effects of the star-forming regions. Those will have effects on kind of disrupting the stability of these prompt cusps. And where they reside, so they would maybe preferentially be outside of the star-forming regions. But we didn't do that yet. So this is maybe a little bit of an optimistic result that we report here. Although in the case of Virgo, I believe that it's okay. But for example, another very popular source to study is a Perseus cluster. And that is also really exciting because it's a CTA target. So you could kind of apply the similar analysis to the higher WIMP masses. But in that case, seeing that the Perseus cluster has AGNs and has star-forming regions and so on and so forth, the modeling of these prompt cusps becomes a little bit more difficult.
All right, last chance for other people. If not, then we can close session.